We grew up believing that the Second World War was won by brave pilots, roaring engines, and sheer human courage. That the Luftwaffe was defeated because the Allies built better planes and trained better men. But buried inside classified after-action reports from 1943 is a truth that almost never makes it into textbooks. At the height of the air war, we were losing. Our early radar systems were blind. Our anti-aircraft guns were guessing. And high above Europe, German crews weren't afraid. They were laughing. They knew the odds. They knew we couldn't see them. Then something arrived from Britain, not a new aircraft, not a bigger gun, a small black box, silent, unseen, that didn't just improve accuracy, it changed the mathematics of warfare itself. This was the SCR-584, a machine that could track, predict, and kill without emotion. An invisible killer that turned the Luftwaffe from a dominant force into a fading ghost in the sky. Tonight, on WW2 Ghosts, we uncover the weapon you were never told about and the moment when war stopped being fought by men and started being decided by machines.
A lot of us look back at the Second World War and think of it as a clash of sheer will, young men in cockpits, iron-sighted anti-aircraft guns, and the roar of the Blitz. But there was a silent, invisible war happening just behind the curtain, one where the stakes weren't measured in courage, but in centimeters and megahertz. By 1943, the Luftwaffe had a secret that made them feel untouchable. They had captured early Allied radar sets, like the old SCR-268, and their scientists had decoded the language of our early warning systems. They weren't just flying through the dark anymore. They were laughing at us. They had developed jammers that could flood our screens with snow, leaving our gunners blind and our cities vulnerable. It felt as though the very air had been reclaimed by the enemy. But what the German High Command didn't realize was that the math of the war had already changed in a small basement at MIT. While the Luftwaffe was busy jamming the long-wave radio frequencies we used in 1940, a group of scientists, driven by a desperate gift from the British known as the Tizard mission, were perfecting the SCR-584. This wasn't just another radar, it was the first microwave killer. By operating at a 10-centimeter wavelength, frequencies the Germans thought were physically impossible to weaponize, the SCR-584 was looking at a version of reality the Luftwaffe couldn't even see coming. Imagine trying to hit a fly in a dark room with a broomstick. That's what anti-aircraft fire used to be, mostly luck and a prayer. The SCR-584, however, introduced something called conical scanning. Instead of a wide, lazy beam, it used a single, squinted radio eye that spun like a top, hundreds of times a second. This allowed it to lock onto a German bomber with the precision of a surgeon's scalpel. The unbeatable Luftwaffe wasn't flying into a cloud of shrapnel anymore. They were flying into a mathematical certainty. At the Anzio beachhead in 1944, the Germans threw everything they had at the Allies, confident their jammers would keep them safe. They were wrong. The SCR-584 didn't just see them through the jamming, it tracked them automatically, feeding data directly into the guns without a human hand ever needing to aim. In one single night at Anzio, these units achieved a 58% kill rate in total darkness. For the veteran pilots of the Luftwaffe, the sky had suddenly become a trap. They weren't being outflown by better pilots. They were being deleted by a machine that didn't know how to miss. This shift from human skill to automated precision didn't just win a battle, it effectively ended the age of the ace and began the era of electronic warfare we live in today. Most of us were raised on the idea that secrets are the bloodline of national survival. You don't hand your best cards to your neighbor, even if you're friendly, because in the game of nations, today's ally is often tomorrow's rival. But in the late summer of 1940, Great Britain did something that on paper looked like an absolute desperation or perhaps total madness. They packed their most guarded scientific breakthroughs into a black metal box, the crown jewels of their empire, and sent them across the Atlantic on a gamble that would define the rest of the century. You have to remember the context of that year. France had fallen. The British Army had been hollowed out at Dunkirk. Every night, the Luftwaffe was turning London into a furnace. Churchill knew that British pluck could hold the line for a while, but it couldn't win a war of attrition against a continent-spanning industrial war machine like the Third Reich. Britain had the brilliant minds, the wizard war pioneers, but they lacked the one thing that turns a prototype into a weapon, the sheer raw industrial muscle of the United States. But there was a problem. The United States at the time was still a sleeping giant wrapped in the blanket of isolationism. To wake that giant, Sir Henry Tizard, a man who understood the intersection of physics and power better than almost anyone, convinced the British government to execute what we now call the Tizard mission. He didn't just want a trade, he wanted a total technological mileage. He argued that if Britain gave the Americans everything, every secret, every blueprint, every hard-won lesson from the Battle of Britain, the Americans would be compelled to build the factories that could save the world. The centerpiece of this black box was a device no larger than a fist, yet it held the power to change the course of human history, the cavity magnetron. To the uninitiated, it looked like a heavy copper block with some holes drilled in it, but to a physicist, it was a miracle. Before this, radar was like a weak flashlight in a thunderstorm, too bulky to fit on a plane and too faint to see small targets. The magnetron changed that. It allowed for microwave radar, concentrating massive amounts of power into a beam so tight it could spot a submarine's periscope from miles away. Therefore, the gamble wasn't just about sharing tech, it was about surrendering a monopoly. When the Tizard mission arrived in Washington, D.C., the American scientists were stunned. They were working on similar problems, but they were years behind the British sophistication. One American historian later remarked that when the British opened that box, they brought the most valuable cargo ever brought to our shores. It was a moment of profound humility for the British. Imagine a master craftsman handing his secret tools to a younger, stronger apprentice because his own hands were too tired to hold the hammer. It was a recognition that the era of the solo superpower was over. By handing over the magnetron, Britain effectively gave the U.S. the DNA for what would become the SCR-584, the proximity fuse, and eventually the very microwave oven sitting in your kitchen today.
But this wasn't a charity mission. Tizard knew that by giving the Americans the how, the Americans would provide the how many. He gambled that American industrialism, the world of Ford, Chrysler, and General Electric, could take a laboratory curiosity and turn it into 10,000 units of battlefield reality. As a result, the Rad Lab at MIT was born almost overnight. It became a hive where British theory met American mass production. If Tizard hadn't been willing to give away the crown jewels, the SCR-584 would have remained a chalkboard drawing in a London basement while the Luftwaffe systematically leveled British industry. It was a lesson in the power of radical transparency during a crisis, a lesson that many of us, in our own lives, have had to learn the hard way. Sometimes, to keep what you value, you have to be willing to share it with the only people who can help you defend it. This surrender of sovereignty created a bond between the two nations that transcended mere politics. It became a special relationship, forged not in the ink of treaties, but in the copper and high-voltage pulses of the magnetron. The sky over Europe was still dark, and the German jammers were still laughing, but because of the Tizard gamble, the invisible math was now being calculated in the safe, well-lit factories of the American Midwest.
We often talk about the miracle of radar as if it were a finished product the moment it left the lab. We're told that it saved the RAF during the Battle of Britain and that it was the secret weapon that won the war. But if we're being honest with history, the kind of honesty you only get when you look at the raw after-action reports, the early days of radar weren't a triumph. They were a terrifying, clunky, and often flat-out failure. To understand why the SCR-584 was such a revelation, you first have to understand the blind giant that preceded it. For those of us who grew up tinkering with radios or fixing our own engines, you know that a tool is only as good as its precision. Early radar, like the SCR-268, was the opposite of precise. It was a massive, sprawling array of antennas that looked more like a giant bed spring than a piece of military hardware. It operated on long-wave frequencies, meters long, not centimeters. But a long-wave beam is like trying to paint a miniature portrait with a 4-inch house painting brush. The problem was fundamental physics. Because the waves were so long, the picture the radar sent back was incredibly fuzzy. A single German bomber at 10,000 feet might look like a massive, indistinct blob on the screen. Worse yet, if two bombers were flying close together, the radar couldn't tell them apart. They merged into one giant ghost. You could tell something was out there, but you couldn't tell exactly where, or how many, or how fast they were truly moving. This lack of resolution created a lethal gap in our defenses. Our gunners were using 3-inch and 90mm anti-aircraft guns that were capable of hitting a target miles away, but they were being fed garbage data. The radar would tell the gunners the plane was in a general area, and the gunners would fill that area with expensive, heavy shells, hoping for a lucky hit. During the early London Blitz, it was estimated that it took nearly 20,000 shells to down a single enemy aircraft. That isn't marksmanship, that's a statistical fluke. The Luftwaffe wasn't just surviving, they were evolving. They quickly realized that these long-wave radars were incredibly easy to fool. They began a practice called windowing, or chaff. German pilots would throw bundles of aluminum foil strips out of their planes. To a long-wave radar, these thousands of metal strips looked exactly like a fleet of heavy bombers. The Allied screens would suddenly light up with hundreds of targets, while the real bombers slipped through the gaps, laughing at the chaos they left behind. But the failure wasn't just in the eyes of the radar, it was in the brain of it. Even if the radar got a decent lock, the information had to be shouted across a noisy airfield to a predictor computer, which was actually a mechanical box full of gears and cams. Then that data had to be manually dialed into the guns. By the time the gunners pulled the lanyard, the German pilot, who wasn't a sitting duck, had already changed course. The blind giant was always swinging where the enemy used to be. This inefficiency wasn't just a technical hurdle, it was a morale killer. Imagine being a young man on a gun crew in 1941, watching your city burn while you fire thousands of rounds into an empty sky, knowing your equipment is being toyed with by a smarter foe. It felt like fighting a ghost with a sledgehammer. The greatest secret of the early war wasn't how good our radar was, it was how desperately close it was to being completely useless. This is the context we often miss in the history books. We think the Allies were always the technological superiors, but for the first 2 years of the war, we were losing the electronic battle. The Germans had the Würzburg and the Freya radars, which were in many ways more sophisticated than our early sets. They had the upper hand because they understood the limitations of long-wave physics. They believed that microwave radar, the kind that could provide a sharp, unjammable image, was a pipe dream because no one could generate enough power at those frequencies. Consequently, the Allied High Command was in a state of quiet panic. They had built a defense system around a giant that was effectively blind in one eye and cataracts in the other. They needed a breakthrough that didn't just iterate on the old tech, but threw it in the scrap heap entirely. They needed a way to shrink the wavelength from meters to centimeters, and they needed a way to make the radar lock on and stay on, regardless of what the pilot did or what aluminum foil he threw out the window. the blind giant era was a period of expensive lessons and tragic losses. It taught the Allies that in modern warfare, close enough is the same as nowhere at all. It set the stage for a desperate search for a new kind of light, a beam so tight and so powerful that no amount of German ingenuity could hide from it. It was the darkness of this failure that made the eventual light of the SCR-584 feel like a genuine miracle from the future. If you've ever spent an afternoon in a workshop, you know there was a world of difference between a blunt chisel and a fine needle. In the world of physics, that difference is measured in wavelength. To understand why the cavity magnetron was the most important invention of the war, you have to understand that the Allies were trying to fight a war with blunt radio waves. They were using waves the size of a house to find an object the size of a garage. It was a mathematical mismatch that was costing thousands of lives. The scientists at the University of Birmingham, John Randall and Harry Boot, realized that to see a German bomber clearly, they needed waves measured in centimeters. Think of it like this. If you're standing by a pond and you throw a boulder in, the waves are massive and slow. They wash over everything. But if you skip a tiny pebble, the ripples are tight, fast, and precise. For years, the scientific world believed you couldn't skip the pebble of a radio wave with enough power to actually detect anything at a distance. The tubes simply burned out.
But then came the copper block, a device that defied the conventional limits of electrical engineering. The cavity magnetron was, in essence, a whistle for electrons. Imagine a heavy block of copper with 6 or 8 circular holes, cavities, drilled around a central core. When you fired a stream of electrons past these holes while applying a powerful magnetic field, the electrons didn't just fly straight. They began to swirl, and as they passed the openings of those cavities, they whistled at a frequency of 3 billion cycles per second. This wasn't just a marginal improvement. This was a jump in power by a factor of nearly 1,000. Suddenly, we weren't just sending out a dim, flickering candle of radio energy. We were swinging a searchlight made of pure, high-frequency lightning. This was the birth of microwave technology. It allowed us to shrink the radar antenna from the size of a billboard to the size of a dinner plate. Therefore, the entire geometry of the war changed in a single afternoon. Because these waves were so small, exactly 10 centimeters long, they didn't just wash over a target, they bounced off it with surgical clarity. A German U-boat periscope, which used to be invisible to radar, now stood out on a screen like a lighthouse. A Luftwaffe bomber, which used to be a fuzzy blob, was now a distinct point of light. But the real magic wasn't just in the seeing, it was in the resolution. In the older long-wave systems, if 2 planes flew closer than 500 yards to each other, the radar saw them as one. With the magnetron-powered SCR-584, you could distinguish between 2 planes flying just yards apart. You could see the difference between the fuselage and the wings. This wasn't just a better radar, it was a new way of interacting with the physical world. For the men 65 and older who remember the first time they saw high-definition television after decades of grainy black and white sets, that was the jump the Allies made in 1943. It was a clarity that felt almost supernatural. One American scientist, upon seeing the first test results of the magnetron in the U.S., remarked that it was the first time we could truly see the shape of the enemy. However, having a brilliant eye is useless if you don't have a brain to process what it's seeing. The magnetron provided the raw vision, but it created a new problem. The data was now coming in so fast and so accurately that human beings couldn't keep up. A human gunner couldn't turn the hand wheels of a 90mm cannon fast enough to match the precision of a 10-centimeter beam. The scale of the universe had indeed changed. It had become faster, tighter, and more lethal than the human nervous system could handle. Consequently, the magnetron demanded a partner.
It needed a system that could take those high-speed pulses and translate them into physical movement without a human being in the loop. It needed the radiation lab at MIT to take this British whistle and build an American robot around it. The Magnetron was the spark, but the SCR-584 would be the engine. It proved that in the modern age, the winner isn't the one with the biggest gun, but the one who can process the most information in the shortest amount of time. By shrinking the wave, the Allies had effectively enlarged their control over the battlefield, turning the vast empty sky into a grid where every German pilot was a marked man. This was the invisible math finally manifesting as a physical reality. The Luftwaffe was still flying the same planes they had in 1940, but the world they were flying in had been fundamentally rewired by a block of copper and a handful of holes. They were no longer fighting men, they were fighting the laws of physics, and physics doesn't take prisoners.
If you've ever worked with a high-torque power tool, you know that speed is dangerous without control. By 1943, the Allies had the speed thanks to the cavity magnetron's microwave pulses, but they were still trying to control that power with 19th-century reflexes. A human being, no matter how well trained, has a processing delay. From the moment your eye sees a target to the moment your hand moves a lever, a few tenths of a second have passed. At the speeds of a Junkers Ju-88 or a Focke-Wulf 190, those tenths of a second translate to hundreds of feet of error. The scientists at the MIT Radiation Laboratory, the RAD Lab, realized that the magnetron had created a crisis of speed. They had a radar that could see a fly at 5 miles, but they were still using human beings to relay those coordinates to the guns. It was a bottleneck of flesh and blood. To win the war, they had to remove the human from the loop. They had to build a brain that could think at the speed of light. But to build that brain, they had to invent a technology we now take for granted, the automated feedback loop. The SCR-584 was the result of this desperate engineering. It wasn't just a radar dish, it was the world's first integrated weapons system. The brain they built was the Bell Labs Mark 9 predictor, an analog computer that lived in a trailer behind the radar, but the real breakthrough was a system called automatic tracking. In previous wars, a radar operator had to chase the target on a screen, manually turning knobs to keep the signal centered. With the SCR-584, the RAD Lab introduced conical scanning. The radar beam didn't just point, it rotated in a tiny high-speed circle, like a finger tracing the rim of a wine glass. If the enemy plane moved slightly to the left, the radar felt the signal get stronger on that side of the circle and automatically triggered a motor to move the dish to compensate. For the first time in history, a machine was locking on to a target. Once the operator found a German plane and caged it, he could literally take his hands off the controls. The 10-foot parabolic dish would follow the plane across the sky with a smooth, eerie precision, like a predator's eyes tracking a rabbit. But the brain didn't just stop at looking. It had to solve a complex calculus problem in real time. It had to calculate where the plane would be 30 seconds into the future, accounting for wind speed, air density, the muzzle velocity of the gun, and the gravity affecting the shell. The RAD Lab engineers connected the radar directly to the 90mm anti-aircraft guns using servo mechanisms. These were high-powered electric motors that received the thoughts from the computer and physically jerked the massive guns into position. Imagine standing on a battlefield and watching a 4-ton cannon move by itself, snapping to attention, pivoting, and tilting with the fluid grace of a dancer, all without a single soldier touching it. To the men of 1943, this looked like sorcery. It was the birth of the robot soldier. The human gun crew was reduced to mere loaders, shoving shells into a machine that was doing all the thinking for them.
The margin for error vanished. The invisible math we discussed earlier was now being executed by gears, vacuum tubes, and electrical pulses. The Rad Lab had turned the sky into a giant automated slaughterhouse for anything that reflected a microwave pulse. They had solved the problem of human frailty by replacing the nervous system with copper wire and the human eye with a spinning beam of energy. This automation changed the psychology of the war. For the German pilots, the experience of being shot at changed overnight. Before, anti-aircraft fire was a barrage, a wall of steel you could try to fly around. Now it was a sniper. The shells weren't just exploding in your general vicinity, they were following you. If you dived, the guns dived. If you banked left, the guns banked left. The SCR-584 was sticky. Once it had you, it wouldn't let go until you were a falling wreck. By removing the human bottleneck, the Rad Lab didn't just improve the radar, they perfected the kill chain. They proved that in the age of high-speed machinery, the most valuable part of a weapon isn't the explosion, it's the logic that guides it. This brain was the direct ancestor of the guidance systems in the missiles we use today, and even the autopilot features in the cars we drive. It was the moment we stopped fighting with our hands and started fighting with our algorithms.
If you've ever been in a situation where you felt like a sitting duck, whether it was a bad business deal or a literal foxhole, you know that the most agonizing part isn't the danger itself, it's the feeling of being unable to strike back. In early 1944, the Allied soldiers huddled on the beachhead at Anzio, Italy, were living that nightmare. They were pinned against the sea, and every night the Luftwaffe would descend from the mountains like clockwork. The German pilots were arrogant. They had mastered the art of jamming the older Allied radar sets, filling our screens with static and snow until our defenses were effectively blind. The Germans believed they had the upper hand because they were fighting yesterday's war. They were using the Duran and Kale jamming transmitters tuned perfectly to drown out the long wave frequencies of the SCR-268. They would fly in, drop their payloads on the crowded Allied camps, and fly away before a single gun could get an accurate fix. It was a turkey shoot, and the turkeys were American and British boys. But in February 1944, a few nondescript olive-drab trailers were rolled off the LSTs and onto the Italian mud, and the Luftwaffe's laugh was about to be cut short. These were the first operational SCR-584 units deployed in a major combat theater. The German pilots, unaware that the math had changed, flew in for their nightly runs. They flipped on their jammers, expecting to see the usual chaos on the Allied side. But the SCR-584 didn't even flinch. Because it operated on the 10-centimeter microwave band, a frequency the German jammers couldn't even reach, the Allied screens remained crystal clear. The Luftwaffe wasn't flying into a fog anymore, they were flying into a spotlight. For the first time, the invisible math was applied to a live, desperate battlefield. The SCR-584 units didn't just see the German planes, they looked back with a vengeance. The operators locked the conical scanning beams on the lead Heinkel and Junkers bombers, and the automated 90mm guns began to track. Imagine the confusion in a German cockpit that night. One moment you're flying a routine bombing run through what you believe is jammed airspace. The next, a shell, aimed not by a tired human eye, but by a relentless analog computer, bursts exactly where you are. Not 100 yards away, not close enough, exactly where you are. The slaughter at Anzio earned its name because of the sheer lopsidedness of the engagement. In one spectacular night, the SCR-584 helped Allied gunners down 12 out of 12 attacking aircraft. In another engagement, 5 German planes were erased from the sky in just a few minutes. The kill rate jumped from the one hit in thousands of shells of the Blitz to an incredible 50 to 60% efficiency. The Luftwaffe's morale shattered. Pilots who had survived years of combat over London and the Eastern Front were suddenly terrified of the Italian night. They began to report that the Americans had developed a death ray or a guided shell. They couldn't conceive of a radar that was immune to their jamming. They didn't realize that they weren't being hit by a new bullet, but by a new way of seeing. For the veterans on the ground at Anzio, the sound of the 90mm guns changed. It wasn't the frantic, rhythmic thump-thump of hopeful fire. It was the sharp, confident crack of a machine that knew exactly where it was hitting. The blind giant had finally opened its eyes, and it was looking directly at the enemy's throat. This wasn't just a tactical victory, it was a psychological turning point. It proved that the Rad Lab experiments worked in the mud and the blood of a real war. It turned Anzio from a potential disaster into a proving ground for the future of electronic supremacy. The Germans had spent the early war years laughing at our greatest secret failure, but at Anzio, the SCR-584 gave the Allies the last and loudest laugh. In the summer of 1944, just as the Allies were gaining a foothold in Normandy, Hitler unleashed his vengeance weapon, the V-1 flying bomb. To the citizens of London, it was the Doodlebug, a pulse jet-powered robot that announced its arrival with a terrifying rhythmic rattle. But the most horrifying part wasn't the sound, it was the silence. When that engine cut out, you had about 12 seconds to pray before nearly a ton of high explosives leveled everything within a city block. For the men defending the coast of England, the V-1 was a nightmare that early radar simply couldn't handle. It was small, it was fast, clocking speeding at 400 miles per hour, and it flew at low altitudes that cluttered traditional radar screens with reflections from trees and hills. It was the world's first cruise missile, and for a few weeks it seemed invincible. The RAF's best Spitfire pilots were literally trying to tip the bombs over with their wingtips because shooting them down was too dangerous and aiming at them was too difficult. But Hitler's terror from above was about to meet the ultimate refinement of the SCR-584, the moment where the invisible math became a perfect shield. In the summer of 1944, just as the Allies were gaining a foothold in Normandy, Hitler unleashed his vengeance weapon, the V-1 flying bomb. To the citizens of London, it was the Doodlebug, a pulse jet-powered robot that announced its arrival with a terrifying rhythmic rattle. But the most horrifying part wasn't the sound, it was the silence. When that engine cut out, you had about 12 seconds to pray before nearly a ton of high explosives leveled everything within a city block. For the men defending the coast of England, the V-1 was a nightmare that early radar simply couldn't handle. It was small, it was fast, clocking speeding at 400 miles per hour, and it flew at low altitudes that cluttered traditional radar screens with reflections from trees and hills. It was the world's first cruise missile, and for a few weeks it seemed invincible. The RAF's best Spitfire pilots were literally trying to tip the bombs over with their wingtips because shooting them down was too dangerous and aiming at them was too difficult. But Hitler's terror from above was about to meet the ultimate refinement of the SCR-584, the moment where the invisible math became a perfect shield.
By June of 1944, the Allies had combined 3 miracles into one singly defensive line along the British coast: the microwave precision of the SCR-584, the automated brain of the Bell Labs predictor, and a new secret called the proximity fuse. This fuse was essentially a tiny radar set inside the shell itself, designed to explode not on impact, but simply when it felt it was near a metal object. The margin for error was reduced to 0. The SCR-584 would pick up a V-1 over the English Channel, lock its conical beam onto the tiny, fast-moving target, and feed the data to the guns. The guns would track the Doodlebug automatically. Because of the SCR-584's precision, the shells weren't just being fired in the general path of the bomb, they were being placed within 30 feet of it. The results were nothing short of a massacre.
In the first few weeks of the V1 campaign, anti-aircraft guns were only taking down about 17% of the incoming bombs. But once the SCR-584 and the proximity fuses were fully deployed along Diver Row on the coast, those numbers skyrocketed. On one single day in August, 104 V1s were detected heading for London. The SCR-584 controlled batteries shredded 68 of them before they even crossed the coastline. Imagine standing on those white cliffs, watching a robot bomb streak across the water, only to see it intercepted by a machine-calculated burst of fire that seemed to know exactly where the bomb was going. It wasn't human bravery that saved London that summer. It was the fact that the Allies had built a faster, smarter robot than the Germans. The invincible terror was neutralized. By the end of the V1 summer, the kill rate for the SCR-584 batteries had reached a staggering 85%. The Luftwaffe's secret weapon had been defeated by a trailer-mounted radar set and a handful of vacuum tubes. The shredder had done its work, proving that in the age of automated warfare, the best defense isn't a thicker wall, it's a more precise calculation. This victory at the coast ensured that the liberation of Europe could continue without the Allied rear being decimated. It was the final proof that the Tizard gamble had paid off. The British had provided the eye, and the Americans had provided the brain and the muscle. Together, they had turned a terrifying new era of missile warfare into a predictable, manageable exercise in engineering. The P-51 Mustangs, or the massive carriers, as relics of a bygone era of steel and oil. They belong to the museums. But the SCR-584 is different. If you could strip away the olive drab paint and the vacuum tubes of that 1943 radar set, you would find the skeleton of the world you inhabit today. It wasn't just a weapon, it was the alpha version of modern life. When the war ended, the invisible math didn't go back into the box. The scientists at the radiation lab and the engineers at Bell Labs and General Electric realized they had unlocked something far more significant than a way to shoot down German bombers. They had mastered the art of high-frequency precision and automated control. But the most immediate impact wasn't in the military, it was in the very kitchen where you probably made your coffee this morning. Percy Spencer, an engineer for Raytheon who worked extensively on the magnetrons for the SCR-584, famously noticed a candy bar melting in his pocket while standing in front of an active radar set. He realized that the same 10-centimeter waves that could see a Luftwaffe wing could also vibrate water molecules in food to generate heat. Therefore, the crown jewel of the Tizard mission, the cavity magnetron, became the heart of the microwave oven. Every time you defrost a meal, you are using a piece of technology that was once the most closely guarded secret of the Allied war effort. Beyond the kitchen, the brain of the SCR-584, those early servo mechanisms and feedback loops, laid the foundation for the Silicon Valley Revolution. Before 1943, computers were mostly static machines that did math on paper. The SCR-584 was one of the first times a computer was tasked with real-time processing. It had to take a chaotic world, translate it into data, and act on that data instantly. This sense, decide, act loop is the direct ancestor of everything from the autopilot on a Boeing 787 to the sensors in your car that help you park. When your vehicle beeps because you're getting too close to a curb, you're experiencing a refined version of the SCR-584's conical scan. The machine is looking back at the world and giving you an automated response. The world became a much smaller, more connected place. The 10-centimeter wavelength didn't just stay in radar, it evolved into the frequencies we now use for satellite communications and GPS. The ability to bounce a signal off a moving object with pinpoint accuracy is why you can look at a map on your phone and know exactly which side of the street you're standing on.